I am T. Mary Rose Mala, Assistant Professor in Mathematics of St.Joseph's College for Women. So in my e-content, I have given a brief description about curvature and radius of curvature. The contents which are described in this e-content are: a small description of curvature and radius of curvature has been given. The geometrical interpretation of the concept has been given. A Cartesian formula has been derived. A problem has been solved numerically, and one of the applications has been discussed. So the pioneers who have contributed to this theory of curvature and radius of curvature are Professor Eugene and Sir Isaac Newton. So curvature and radius of curvature are nothing but they are measures like length, time, mass, etc. So before getting into the concept of curvature, we should know what do we mean by a curve. So a curve is nothing. It is almost similar to a straight line which does not have any sharp turns. Before getting into the concept of curvature, so let us understand the geometrical meaning of curvature. So over here, there is a curve y is equal to f of x, and on the curve we are having a circle. So this circle has been obtained when this curve curves again and again, or when it bends again and again. This curve results into a circle. So initially we are having a curve y is equal to f of x, and at a point P we are having a tangent. The length of AB is given by S, and the angle made by the tangent MN with the x-axis is alpha. So similarly, as the point P moves along the curve at Q, again we are having a tangent at Q, and the tangent at Q makes an angle alpha plus delta alpha with the x-axis. Now the distance between A and Q is nothing but S plus delta S. Now again the point Q is going to move to another point R. Again we are going to have a tangent. So as the point is going to move along this curve, the curve is going to bend more and more, and finally it almost ends up with a circle. So this circle is called as circle of curvature, and this process of bending of a curve is called as curvature. So now we can give the definition for curvature. Curvature is nothing but it is a measure in which there is a gradual increase in the change of direction of a point that moves along the curve, or also it can be defined as a measure of the unit tangent vector which rotates along the curve. So again there is a geometrical interpretation of curvature and radius of curvature. So again we are having a curve y is equal to f of x. We are having a tangent at P. We are having a tangent at Q, and the angles made by the tangents at P and Q are alpha and alpha plus delta alpha. So now over here curvature is nothing but it is the rate of change of the angle with respect to the arc of the length, and the formula is nothing but 1 by rho is equal to d alpha by ds. Similarly, the radius of curvature is denoted by rho, and it is nothing but the rate of change of the arc length with respect to the angle. So the formula for a radius of curvature is rho is equal to ds by dx. A Cartesian formula for radius of curvature has been derived. We know that the slope of a line is given by dy by dx is equal to tan alpha. So now if we differentiate this equation, we will get d squared y by dx squared is equal to secant squared alpha d alpha by dx. So as we know, the formula for radius of curvature is ds by d alpha. We've got to introduce the parameter s. So I am writing d alpha by dx in terms of s as d alpha by ds into ds by dx. So from this diagram, if the length of PQ is given by delta s, then delta x by delta s is nothing but it is cos alpha. So cos alpha is dx by ds. I am substituting the value for ds by dx, which is 1 by cos alpha. So thereby we get the value secant cubed alpha d alpha by dx. We also know that secant cubed alpha is nothing but (1 plus tan squared alpha, the full part whole cubed). So secant alpha is nothing but root of 1 plus tan squared alpha. So that is what is substituted over here. So tan squared alpha is nothing but it is dy by dx the whole square. So thereby the formula for radius of curvature is 1 plus dy by dx the whole square, the whole part 3 by 2 divided by d squared y by dx square. So the formula for radius of curvature is 1 plus dy by dx the whole square, the whole part 3 by 2 divided by d squared y by dx square. So when dy by dx tends to infinity, then the formula is changed as rho is equal to 1 plus dx by dy the whole square, the whole part 3 by 2 divided by d squared x by dy squared. So numerical problem has also been evaluated. So now we have got to find the radius of curvature for the curve y is equal to e power x at the point 0, 1. So for all the problems we've got to find the value of dy by dx and d squared y by dx squared at the particular point and substitute it in the equation. So over here the given curve is y is equal to e power x. On differentiation it gives e power x, and at the point 0, 1 its value is 1. So on differentiating e power x, once again we will get the value as e power x, and its value is at 0, 1 is e power 0, which is again equal to 1. So on substituting these values in the formula, we will get the value of radius of curvature as 2 root 2. So for all the problems we could find dy by dx, d squared y by dx squared, and substitute it in the formula. Going on to applications of radius of curvature and curvature, there are various applications. So we can apply it in the case of root canal treatment, we can apply it in grinding wheels, and also in the case of designing railway curves and road curves. So this curvature and radius of curvature plays an utmost role and a significant role in the designing of curves along the roadways and railways. So the National Technology Standards also advises us to use transition curves. So a transition curve is nothing but a curve which follows all the rules of curvature. So in a transition curve, the radius of curvature always increases from 0 to a higher value. So when the radius of curvature increases, the curvature will decrease, and thereby there will be an ease to travel along the curves. So when traveling by means of a car along a curve, we always have to have a transition curve, or the road should be designed in the form of a transition curve. So because a centrifugal force will be produced when the car is traveling along the curve. This centrifugal force will pull the vehicle outwards, and it will result in a jerk and in a disturbance. So in order to avoid this, we must always have a transition curve along road curves in order to avoid this difficulty. So over here also the radius of curvature will be increased, curvature will be decreased, and there will be an ease in traveling along the curve. In the case of railways, there is a great relationship between radius of curvature and the railway curves. So when a train is moving along a curve, there will be a heavy noise, and in spite of that there will be a wear and tear in the wheel as well as in the rails. So over here also it is advisable to design the curve in the form of a transition curve. So over here mainly the transition curve which is prescribed in the case of railways will be a cubical parabola, whose equation is nothing but y is equal to x cubed. So in a cubical parabola there is a gradual increase in the radius of convergence from 0 to a higher value. So there will be a feasible movement of the train as it moves along a curve. This is explained by means of a small derivation. So just imagine the train is moving along a straight track. So when the train is moving along the straight track, the value of x is 0, the angle will be 0, all the values will be 0. Now when the train is gradually moving along the curve, say it attains a distance L, and over here we'll have a small angle alpha. So over here, I'll take the value of x as L and the radius of convergence as capital R. So if I multiply x into R, I'll get a constant value LR. So from this, I can determine a value for 1 by R. So similarly, we know that the curvature is given by 1 by R is equal to d alpha by dx. By using simple integration, I determine the value of alpha as x squared by 2RL plus a constant value. By using the initial conditions, at x equal to 0, alpha will be 0. So naturally the constant value will be 0. And also we know that the value of dy by dx will be the angle alpha. So over here we'll have dy by dx is equal to x squared by 2RL. So again, by using simple integration, we can evaluate the value of y as x cubed by 6RL plus a constant. Again, by using the initial conditions, the constant value becomes 0. So thereby, the equation of the cubical parabola is y is equal to x cubed by 6 into capital R into L, where R is the radius of curvature. So over here, we can find that the cubical parabola is in terms of 1 by R. So initially the value of y was 0 and now it has been increased in terms of 1 by R. So there is an increase in radius of curvature and there will be a decrease in curvature, and thereby the train can move feasibly towards the curve. So thereby we are preferring to use the transition curve to be a cubical parabola. So these are all the small descriptions regarding curvature and radius of curvature. Thank you.